is my second ECG video. Today I'm talking about the conducting system of the heart, ECG interpretation format, heart rate calculation, and how to calculate the ACEs. Okay, let's start here. So the first is the conducting system of the heart. Let me draw the structure of the heart. Okay, and the conduction starts from the SA node, then it goes to the AV node. At the same time, when it's going to the AV node, it also trying to depolarize the right and left atrium. So right atrium, SA node is located at the right atrium. So like right atrium, and then to the left atrium, it conduct to the Bachmann bundle. It is the bundle of Bachmann, B-A-C-H-M-A-N-N, Bachmann bundle, and then it reaches there LA node and causes depolarization. Okay, when it reaches the AV node, it has some pause and then go down to the bundle of His, and sorry. Is the interventricular septum and LV mass and RV mass. Okay, so go down to the bundle of His, and in the interventricular septum, the direction of the depolarization is usually from the left to right. Goes through this direction, and then it goes to the left bundle branch and right bundle branch. In the left bundle, it has two bundle. Actually, it's starting from here. It is the anterior vesicle and posterior vesicle. It is the anterior vesicle and it is the posterior vesicle. It is the left bundle branch. Left bundle branch. It is the right bundle branch. And in the bundle branch, it goes, the depolarization goes from the endocardium to epicardium through the Purkinje's fibers. Okay, so started at the SA node and then go to the AV node and bundle of His, and then left bundle branch and right bundle branch, and Purkinje's fibers ended in the Purkinje's fiber. It is the conducting system of the heart. Okay, SA node usually depolarizes at the rate of 100 beats per minute, but the heart rate is, in most of the Boston, heart rate is less than 100 beats per minute, because SA node is always under the Vg tone. Because of the Vg tone, the heart rate reduces to around about 72 beats per minute. Okay, and another thing we have to know is the LV wall thickness. LV wall thickness is 3 times the RV wall. 3 times the RV thickness, and septal depolarization goes through the left to right. Left to right. Ventricular muscle depolarization go from the endocardium to epicardium. Okay. So when we look at from the V1, V1 is usually placed on the chest, V1 to V6 is on the chest. When we look from the V1, and the V1 is from this side, and V56 from this side, you see? Okay, I will show here. V56 here from the left side, and V12 from the right, the relatively right side. So, okay, so in the V1, at first, due to septal depolarization comes from the left to right, so towards the V1, V2. So it is like upward deflection. Positive deflection means the electricity comes towards the electrode. So these electricity, in the septal depolarization, electricity comes to the V1 to V2. So for the V5 and V6, it goes downwards. It goes downwards. It's the opposite side of the electrode. Okay, and then so the first part of the QRS complex denotes the septal depolarization, and the second part, they depolarizes simultaneously. Right and left ventricle depolarizes simultaneously, but left ventricular mass is bigger than the right ventricular mass, so it obscures the right. So the net ventricular depolarization is here, in this direction. Left is bigger. So in the V1 and V2, it is like negative deflection, and for the V5 and V6, it is towards the electrode, so positive deflection. Okay, you see? So, so V3 and V4 are in the middle position. Okay, so it means there is a upward positive progression of the R wave, from the V1 to V5-6. The first stroke of the first part of the QRS denotes for the septal depolarization, and the second part is the ventricular depolarization. Since left ventricular is bigger than the right ventricle, the net effect is towards the V5, V6. That's why there is main negative deflection in V1 and 2, and main positive deflection in the V5 and V6. So during the septal depolarization, it is towards right, towards the right. So V1, V2, positive, V5, V6, negative deflection. For the ventricular depolarization, LV mass is larger. So V1 and V2, so V1 and V2 negative deflection, V5, V6, positive deflection. And this can also explain the reason why there is R wave progression towards the V5 and V6 in normal ECG. Okay, and so let me add some more. So what does the wave in the ECG means? So P is for the atrial depolarization. Q is really for the septal depolarization. RS is for the ventricular depolarization. And so you can, that there is a T is for the ventricular repolarization. So you can ask me that, where is the atrial repolarization? But there is no way for the atrial repolarization. Actually, atrial repolarization is abandoned in the ventricular depolarization. It is in the QRS. And U is not always there. U denotes the slow repolarization of the Purkinje fibers. So where can you find the Q? It will discuss later. Okay. may be present or absent, but other waves are usually present in the ECG. Okay, so ECG interpretation format. The first thing we have to know is the identification. Identification, that is, we have to check whether we are doing the ECG for the correct day, age, sex, and we have to note down registration number, date and time, and we have to compare with the previous ECG if necessary. Okay, name, age, sex, registration number, date and time, and compare. Okay. The second one is the check sensitivity. You have to check voltage and paper speed before reading the ECG to avoid unnecessary errors. Okay, the third is the heart rate calculation. Four is written assessment. 5, ACEs calculation. And then we will go through the single waves like P wave. We have to look for the P wave abnormality, PR interval, and segment, QRS complex. And at the same time, we have to look for the ventricular hypertrophy criteria, ST segment, QT interval, T wave, and also changes specific to specific diseases. Okay, there might be many ECG formats, but this is the one I usually adopt. And the number 12, changes specific to specific diseases, means like J waves and hypothermia. It is usually not in the PQRST or but J waves, epsilon wave, like that. Okay, so it will miss the since you check the waves, segment, and interval step by step, it will miss the single thing. Okay, so identification is the first step, what we need to know. The second step is the check sensitivity. Check voltage and paper speed. Okay, voltage mean the height of the ECG, usually height or width, height or depth of the ECG, and paper speed is the width of the ECG waves, that denotes the waves of the ECG wave. Because let's start with the paper speed. Usually the standard paper speed for every ECG is 25 millimeter per second. So that means 25 millimeter in 1 second. So 1 millimeter is 1 by 25 seconds. That means 0.04 second. Okay, 1 millimeter in the ECG, we usually did do it with it is the 1 millimeter. So 1 millimeter is the one small square. One small square is the 0.04 second, and that is also 40 millisecond. And 5 small square, that is one large square. One large square is the 0.2, and 0.04 into 5, it is the 0.2 second. It has the 200 millisecond. So how about the, it is the 0.2 second. 0.2 second in is one large square. So 1 second. 1 second is 0.2 into 5, 1 second. So 1 second is 5 large square. Okay, to get one, do you understand? To get one, we have to multiply with 5, so multiply with a 5, so 5 large square. Okay, so 6 seconds is there, 5 into 6, 30 large square. So usually we use this as a long lead 2. I shall long lead 2 for the 6 seconds, 30 large square. We usually record 30 large square for the long lead 2, and we make the number of the R waves in the 30 large square, and for the 1 minute we need to check the heart rate, and so for the 1 minute we have to multiply with 10. So 1 minute 60 seconds is equal to 30 into 10, 300 large square. So long lead 2 is the number of large square in long lead 10. That means, so after we have done the long lead 2, that is after we have recorded the 30 large square, we have to count the number of R in that long lead 2 and have to multiply into 10 to get the 1 minute heart rate. Okay, so it is how to calculate that. What is the standard paper speed, and abnormality is the abnormality in the there might be some, if there is some paper speed abnormality, if it is longer than the 25 millisecond, like 50 millisecond, the ECG will become double the normal distance normal width, and if it is shorter, the ECG will become very fast down. Okay, so it is the normal paper speed. 0.04, 1 small square represent 0.04 second, 1 large square 0.2 second. Okay, in this case, and so we have to look at the state of the sensitivity point. It is usually in the like that. A paper speed of 25 millisecond is like that, but in this case it is 2 large square. That means that double the normal paper speed, so it is 50 millimeter per second. So the heart rate is very slow. There is 12 large square between the 2 R. So the heart rate is very slow, and we have to check that sensitivity issue before calculating, before looking for the ECG changes. So it is we have to divide the distance between these 2 R, because the paper speed is 50 millimeter per second. Otherwise, another thing is that it is half the normal paper speed. Normal paper speed is like here. Now it is 12.5. So there is some AF here. Okay. The heart rate is very fast. So we have to multiply by 2 before concluding that there is the tachycardia. Okay, there is the heart rate. For the voltage, for the voltage, 1 centimeter, that is 2 large square mean 1 millivolt, and 1 large square mean half, so 0.5 centimeter or 0.5 millivolt, and 1 small square mean 0.1 centimeter or 0.1 millivolt. 1 millimeter. Wow. Yeah, And so in this case, actually normally it is the normal 1 millivolt and 25 millimeter per second. So here it is 2 large square, that is 1 millivolt, is the normal voltage. But in this case, it is only 1 large square. So the height of the ECG waves are half the normal. 1 millivolt causes the deflection of 0.5 centimeter, only 0.5 centimeter. We have to draw with the 1 centimeter with 1 millivolt. So the ECG, we have to multiply with 2 for the ECG height and depth. Okay, all the complexes are small here. For this, instead of the 2 large square, it is drawn with the 4 large square. So the ECG waves are very deep and very high, and so we have to divide it by 2 for these ECG waves. It is the over calibration. We use this as a calibration. It is the over calibration, and each line deflection of the 2 centimeter. All the complexes are large compared with the ECG recorded in the correct calibration. Okay, so the first thing is how to calculate the heart rate. Heart rate calculation. If you have the regular rhythm, heart rate is 300 divided by number of large square between 2 consecutive R. Do you get that? Or 300 divided by 2 consecutive R. But if the heart rate is very fast, and you can use 1500 divided by number of small square between 2 consecutive R. Okay, it is for the regular rhythm. For the irregular rhythm, heart rate is the number of R in long lead 2, that is 30 large square, 30 large square into 10. Okay, it is only 300, so that's 300. Okay, so it is, if depending upon your heart rate, it is whether regular rhythm fast, you should use this one. If it is the regular rhythm with the not very fast, so you can use here. If it is the irregular rhythm like atrial fibrillation, you can use this long lead 2 method. Okay, so it is the how to calculate the heart rate. So another thing is the how to calculate the ACEs. There are 4 methods for ACEs calculation. Number 1 is the quadrant method. It is very simply used. Number 2 is the 3-lead analysis. 3 is isoelectric lead method. And 4, it is SAM analysis. It is super ACEs man analysis. Okay. Actually, it is there. So the term ACEs means that we have learned it from the mathematics when we are in the high school. Axis means the x-axis and y-axis. Usually the axes are perpendicular to each other. So 1 in the ECG waves, 1 and AVF are the perpendicular lead. And so we usually use the 1 and AVF to measure to calculate the ACEs. Okay, but normal ACEs is not more than that. Normal ACEs is ranging from the -30 to +90, not between the 0 and +90. We usually call the term, actually that is deviate from the ACEs, that this here 0 to -30 is deviating from the normal ACEs, but we usually use it as a physiological LET. We can call it normal. we can call it normal. But if it is rotating here, it is left axis deviation. So it is the left axis. It is between the -30 and -90 degree. For the right axis, it is between the +90 and 180 degree. For the extreme axis deviation, it is really like the head is upside down. So it is the extreme axis deviation. And for the LED, it is rotated left, like your heart is here. It is rotated left, LED, rotated right, RAD. But extreme axis is like upside down. So it is use the term called extreme axis deviation. And otherwise, it is north and west. So it is also called the northwest axis, northwest axis. And so quadrant method is the easiest method to use, but it doesn't distinguish between the physiological LET and pathological LET. So since the perpendicular leads are lead 1 and lead AVF, we use these two leads for the quadrant method. And so 1 and AVF. Normally, it has to be for the one, okay, sorry. Okay, heart is here, and so electricity is downwards here. So electricity is in the normal, electricity comes both towards the 1 and both AVF. Okay, so in 1 towards the electrode, so upright. In AVF, it is also towards the electrode, so upright. It is normal. It is okay. In case of LAT, MS here. So it is towards the 1, but it is away from the AVF. It is right here. So AVF. So it is the LAT. And for the RAD, it is like here. The direction is like here. So it is towards the AVF, but away from the 1. So away from the 1. Away from means the negative deflection, towards means positive deflection, you know that, towards them, AVF, so RAT. So this is what we obtain from the quadrant method, and we can use the simple mnemonic leave and reach. Normal, it has to be upright, both upright. For the LED, 1 and AVF are leaving each other. So LAD, it is reaching. So RAD. For the extreme axis, the direction is like this. Okay, very messy here. The direction is like this, and so it is away from the 1 and away from the AVF. So in the extreme axis, it is away from the 1, away from the AVF. So both down. Okay, it's here. Direction, positive, 1, positive, leave. Reach, negative. Okay, but we use the term possible LAT, not like RAD. RAD is sure, because we use the term possible LAT because there is some physiological LAT or pathological LAT. Physiological LAT is what we use there, what we call it within the normal axis. So we use possible LAT. So we cannot distinguish physiological LAT and pathological LAT, that is between 0 to -30 and -30 to -90 degree by quadrant method. So we use another method called 3-lead analysis. In 3-lead analysis, we put on lead 2. Apart from that, lead 1 and previous lead 1 and AVF. Okay, so in lead 2, if the lead 2 is, okay, others are also, everything is the same. For the normal axis, it is the same. For the RAD, negative, positive, positive. Extreme axis, negative, negative, negative. Okay, but for the physiological and pathological, it is equiphysite here and negative here. So that means lead 1, 2, AVF, and so LAD in the quadrant mean. Okay, so it is LAD. But if the lead 2 has more positive deflection or equiphysite mean the same length of the positive and negative deflection. So it is called the physiological LAD. But if lead 2 has more of negative depression, okay, there's more of negative deflection. Here there is some positive deflection, but negative deflection is deeper. So it is the pathological LAD. Can you see that? If lead 2 have more of positive deflection or equiphysite, it is physiological LAD. If lead 2 have more of negative deflection, it is pathological LAD. It is quite simple. Okay. Here, what is using for equiphysite? Okay. So, isoelectric lead method is that method, isoelectric lead method. It is quite difficult. You have to, step 1, you have to find the isoelectric lead. Isoelectric, that means that flat QRS with no positive and negative deflection. Sometimes there are such kind of leads, like this kind of leads, no positive and negative deflection, just flat QRS. It may be seen in the lead 1 sign in COPD, like no positive and negative deflection, or equiphysite lead. Equiphysite lead mean the similar length of positive and negative deflection. Here, lead 2, it is more on negative deflection. It is more of positive deflection, more positive, more negative, more positive. But in the lead 2, it is almost the same. The length, positive and negative deflection is almost the same. So it is the lead 2 in this case. Okay. Step 2, lead 2. We have to lead 2 here. Okay. Step 2 is add or subtract at n and subtract 90 degree to above lead. Okay, so lead 2 is plus 60 degree. We all know that. So at plus 90, so plus 150. Subtract minus 90, so minus 30. Okay, okay. Then that is step 3. Find most positive lead. Most positive lead. So most positive lead is the tallest R with the smallest S. So here, the positive lead here is the 3 AVF and AVR, but there is some negative deflection here. There's also there is almost no negative deflection. So most positive lead is the lead 3. Okay, most positive lead is the lead 3. So lead 3. Step 4, cardiac assist is there at the direction of positive lead. So we have to choose which one is most nearest to the lead 3. We have step 1, we have find the equiphysite lead, that is lead 2. That is the positive and negative deflection length is almost similar. Okay, step 2, we have to add and subtract the degree, 90 degree to the previous lead. So plus 150 and minus 30. Step 3 is we have to find the most positive lead. It is the lead 3. So this, from this 150 plus 150 or minus 30, we have to choose the one that is deriving the axis, real axis. So it must be most nearest to the step 3. It is lead 3. So we know that lead 3 is in the direction of lead 3 has 120 degree. You know, lead 3 has 120 degree. So 150 and plus 150 and minus 30, which one is more nearest to the 120? So it is the nearest to the 120. So the answer here is plus 150 degree. Okay, can you get that? Step 1, find the equivalency or isolateral lead. Then add and subtract 90 degree to the above lead. The answer will be one of the results, one of these results. Okay, so we have to choose which one is the answer. So we have to choose the most positive lead. The answer is the degree which is most nearest to the positive lead. So in this case, the most positive lead is plus 120. So plus 150 is the answer. It is the isolateral lead method. It can estimate almost the similar degree of the cardiac axis. Okay, so another method. Another method is the SAM analysis, super axis man SAM analysis. So first we have to note the net positive deflection of lead 1. We use the 1 and AVF for this method. Okay, so like this. Maybe the small square, we have to count the small square. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it is the plus 8. 1, 2, 3, 4, 5. Okay, so minus 5. So net is the plus 3. You know, okay, we have to note that it is the lead 1. Note the net deflection of, net positive or net deflection of AVF. Okay, so if it's the AVF is like that, 1, 2, 3, 4, 5, 6, 7, minus 7 plus 2. So net is the minus 5. Okay, then plot on axis. Okay. 1 here, 1 AVF here, or positive here, positive here, negative, negative. For the 1, it is plus 3, 1, 2, 3. It is the plus 3. Okay. For the AVF, it is minus 5, minus 5. So minus is up. 1, 2, 3, 4, 5. Okay. So we have to cardiac axis in this degree. So 1 and AVF, it is according to the first quadrant method, 1 upright, AVF downward, so leaving each other, so left axis deviation. In this case, it is also pointed towards the left axis. Okay, so we can measure the degree. We can use the degree measurement. Whether here is the correct exact degree. We can know the cardiac axis and exact degree. Yeah. Okay. So it is the SAM analysis. So it is the end of this today video. Today we have discussed about the conducting system of the heart. Conducting system of the heart. Why there is airway progression, what denotes the septal depolarization, what denotes the ventricular depolarization. LV mass is really larger than the RV mass, and what denotes each wave, and ECG interpretation format, and how to check the voltage and paper speed. Standard paper speed is 25 millimeter per second, and standard voltage is 1 millivolt is 1 centimeter. Okay, so what is the effect of low paper speed and high paper speed? What is the effect of over-calibration and under-calibration? Okay, heart rate calculation for the regular rhythm, fast and slow, normal, irregular rhythm, and then axis calculation in quadrant method, 3-lead analysis, isolateral lead method, and SAM analysis. Okay, I hope it would get you